Okay. It works, I can. But wait, I can put it in the pocket, okay? Oh, okay, so you can think of parameter as typically it would be either high dimensional vector, okay, high dimensional vector, or a large matrix, okay. In fact, such as, for instance, covariance matrix. In fact, later on we will deal a lot with examples related to covariance matrices, since this was my motivation, okay, primary motivation to study this problem. And the functional itself, you can think of, for instance, something analytically given. It could be a norm on the space, okay, of vectors, okay, or it could be something related to spectral properties of the matrix. For instance, you know, the difference between first and second eigenvalue, okay, between the top eigenvalue and the next from the top, okay, for instance, the gap, okay, something like this, okay, or some other reasonable functions of eigenvalues or something related to eigenvectors of matrices, okay. But I maybe would even prefer if we have a little bit more vague view of the problem, okay, so we will kind of think of f of theta as some one-dimensional feature, okay, that is of interest to you. So you don't want to estimate parameter as a whole, but rather you want to estimate certain specific feature, okay, associated with this complex parameter, okay, and you have some general knowledge about what kind of feature it is, and it's encoded by this condition that the functional comes from certain class, okay? For instance, you can think of features that smoothly depend on the parameter in some sense, okay? And other than this, the functional is given to you in the sense that you can ask some oracle, okay? What is the value of this functional at a point of your choice? In the parameter space, you can choose maybe several points. Probably you should choose points that depend on the data, okay? And then based on this information, based on the values of the functional, at this point, you want to estimate the value of the functional known parameter theta, okay? That would be the way I will I will move it with this. So more formally, okay, what we will be thinking about, we will be interested in this quantity, okay, which is a solution, if you wish, of max, min, max problem, okay? So what you are looking at minimax risk of estimation of the functional, okay, of the value of the functional at theta. So this is mean squared error of certain estimator, then you take supremum over all values of the parameter in the parameter space, and then you take infimum over all possible estimators. So this is minimax risk. And then you're trying to determine what is the worst minimax risk for the functional in the class, for least favorable functional in the class, right? And we want to know the size of this quantity, okay? We want to know the size of this quantity. Moreover, we want to try to construct some estimation method, okay, that would allow us to create estimators for any given functional from the class for which this risk is attained, say, okay, for which we can get at least as good as this risk suggests, okay? And often in this type of problems, it's possible, not always, but often it is possible to achieve kind of classical error rate of estimation of the functional, because functional is just a one-dimensional feature. It's not the whole parameter, okay? And we might maybe hope sometimes that it is possible to achieve a rate of the order n to the power -1. And the question is when it is possible. And in particular, we will be looking at classes of smooth functionals and try to determine the threshold on the smoothness such that when we are above this threshold, we can estimate the value of the functional with parametric rate. And if we are below the threshold, the rate can be slower, okay? But we want to describe this phase transition, if you wish, in this problem between slow and fast rates, okay? Oh, okay, so kind of we can look at sort of a classical version of this problem that essentially goes back to Fisher, okay, to something that Fisher knew already in the 20s. So this was when Fisher looked more like this, okay, than like this. Okay, Fisher was looking at what we call now regular statistical model. He cared about certain regularity properties. So regularity basically means that we can define what we now call Fisher information matrix. Okay, so there is enough smoothness. Okay, in the model that allows us to define the score function and to define the covariance of the score function, which is called Fisher information matrix. Okay, in statistics and we want Fisher information matrix to be non-singular, okay? This is usually part of standard regularity assumptions in statistics, okay? And then there is a continuously differentiable function. You don't need more in this setting, right? And we want to estimate f of theta based on the data, okay? Now we are assuming that the problem. But so what Fisher would do in this situation in order to solve this problem of estimation of smooth function, Fisher would use his maximum likelihood method. So he would he would compute maximum likelihood estimator, okay, estimator that maximizes this product, okay, and then he would use plug-in estimator based on maximum likelihood. And in this case, it was already known to Fisher, but it was proved kind of rigorously later, okay, under proper regularity assumptions, the means error multiplied by n would converge to this limit variance, okay, which is defined in terms of the inverse of Fisher information and in terms of the derivative of the functional or gradient of the functional. And also we will have asymptotic normality of the plug-in estimator, okay, asymptotic normality of the plug-in estimator with this limit variance. And this would mean that this quantity that is of interest to us for a class. No. So we can so in this case, we just you can use an estimator that is based on just plug-in. So we choose just one point in the parameter space that depends on the data, maximum likelihood estimator, and we are getting decent behavior. And moreover, Fisher already in the 20s, he claimed that this solution is optimal, or as he would say, asymptotically efficient, okay? By asymptotic efficiency, Fisher meant the following, that if you use any other estimator that is also that after normalization with square root of n, this estimator would converge to some normal distribution with some variance. Then this variance would not be better than for his maximum likelihood estimator, okay? If you use any other estimator of this, not necessarily based on any plugin, whichever estimator you can invent, it would not do better, okay? That's what Fisher claimed, okay? A just differentiable function, okay, nothing, continuously differentiable. You don't need anything more than this. Now, Fisher claims this, okay, I am not telling conjectures. He never conjectured anything, he just claimed that it's the best estimator and that's it, okay. So he claimed this. He could not prove it, of course, okay, in any reasonable way back then, because proof of such type of facts are usually information theoretic in nature, and also Fisher introduced Fisher information, but it was maybe 50 years before the information theory was developed, and moreover, probability in the early 20s when Fisher was doing this was not a rigorous mathematical subject yet, okay? It was only becoming a rigorous mathematical subject, so it was just impossible to prove anything like this, but Fisher had, kind of, was, how to say, audacious, okay, or something like that, or ambitious, or whatever, okay, and he made these claims all the time, and he had rather powerful intuition, and often he was right, okay. So formally, he was not right, okay, because under the conditions he stated this, it's not true, okay, what he stated. It was discovered immediately. Wishart, for instance, wrote a letter to Fisher where he immediately came up with counterexample. Fisher replied that it's rubbish, because of course I meant that there should be this condition that immediately ruled out Wishart's example, okay? But then other people came up with other examples, okay? And it took 50 years before it was in the early in the 70s, actually, already 50 years, when Fisher died already, okay? Uh, this is what is called local asymptotic minimaxity. Okay, this was proved by Hayek and Lecam. It's a classical result now in asymptotic statistics, and this is in which sense precisely Fisher's claim is correct. Okay, so they managed to prove that if you consider minimax risk over kind of small neighborhood around some point theta naught in the parameter space, then under regularity assumption, this limits will be greater or equal than this variance defined in terms of the inverse of the Fisher information, right? And now, if you combine this, what Fisher really knew about convergence of properly normalized mean squared error of plug-in estimator, right? This tells you that this estimator indeed is optimal in this sense, okay? It's, kind of Fisher's asymptotic efficiency becomes local asymptotic minimaxity of this plug-in estimator, okay? And so in this situation, the problem is solved already, okay? There is nothing to do here, okay? You just have to use maximum likelihood estimator and plug it in the function, okay? But in the early 70s, when this result was obtained, already people were pretty much interested in non-parametric statistics, okay? So in the problems when the parameter is infinite dimensional, okay? And they started trying to figure out whether anything like this can be established in this case under certain assumptions on the functional. They were working a lot with specific examples of some integral functionals in the 70s and things like this. And they pretty soon discovered that, okay, sometimes the error rate of the order 1 over n is achievable, sometimes not, okay, depends on the functional often, okay. Now, estimation method, you could hardly expect that plug-in estimator, when you plug in maximum likelihood in your functional, would work. Estimator methods usually, even if you can achieve rate n to the power -1 estimation method usually becomes rather complicated, okay? Rather complicated, so it's not an easy problem at all, okay? And there are many papers written often about very specific functionals for which you need, to develop, to write 50 pages paper and develop a lot of theory just to understand what exactly is happening with one particular functional, okay? Now, this is one example of the problems. So, it's a paper. So certain ways to characterize complexity of compact subset of L2, and they were using for this Kolmogorov widths. Okay, yeah. And then some threshold on the smoothness of the functional you want to estimate. You want to estimate not the whole parameter, but just some feature, okay, some smooth function of the parameter. And they discovered that there is a threshold on the smoothness of the functional such that if you're above this threshold, you have square root of n rate, and moreover, you estimate your functional asymptotically efficiently, so not only with optimal rate, but with optimal limit variance also, okay? And if you are below this threshold, then efficient estimation becomes estimate. Okay, so that was kind of this were the results in these papers. Okay, so what I will be talking about. Oh, the motion of smoothness I will use in this problem. Let me give you this definition. So we will be looking at functionals defined on a subset of linear norm space, Banach space. Say, if we assume that this function takes value also in a Banach space, then there are these kind of basic norms that you can define. Okay, that measure the size of your function. You have sup norm, you have Lipschitz norm that quantifies the Lipschitz condition on the function, and you have this, I don't know what it, Lipro norm that quantifies the Hölder condition of the function with exponent rho, okay? So it's kind of, oh, if your function is on the top of it k times differentiable, I mean differentiability by differentiability for shadow differentiability for some k greater or equals than 0, then you can define the degree of smoothness as k plus rho and define the CS Hölder norm, okay, on your functionals. That is defined in terms of these three basic norms this way, okay, but we are putting these norms now on the derivatives, right, of our function, right? There is one thing that one has to have in mind in these problems, okay, since we will be looking at high dimensional and infinite dimensional spaces here, okay. What is the J's order Frischer derivative? J's order Frischer derivative at some point x of our functional g, right, will be a J linear form, right? A J linear form. You kind of can think about H2 a multilinear form. And then what is the most natural way to measure the size of multilinear form? You would just use what is called operator norm in this case. So you take supremum of the values of the form or this H is coming from the unit ball, right? Coming from the unit ball. This is the most natural way to define it, like this. And we will be using this norm. this way. Okay, we'll be using operator norms here for this purpose. So if you look back here, so if you look at things like this, right, when you are trying to define, say, Lipschitz norm, for instance, of the derivative, you have to work with operator norms here, because you write j of x minus j of y, right, and this will be multilinear forms, and you have to measure the difference, and you will measure the difference by operator norm, okay? It's kind of, we rarely think about this when we talk about Hölder smoothness for functions on R2, but this is because it's completely irrelevant which norms we are using, okay, in this case, because when the space is finite dimensional or fixed dimension, all norms are equivalent then, and then it's everything is the same up to constant. But if you are in infinite dimensional space, you will have completely different smoothness classes, okay, if you define norms differently. So this we have to have this in mind, okay, anyway. Okay, so yeah, so you can write, of course, for these Hölder smooth functions, Taylor expansion. On order k, it will look like this, with a remainder that satisfies this bound, okay? That satisfies this bound, and we will be using this, okay, once in a while. I probably have to start moving a bit faster because, I have slides that I used, I kind of, last year I was on sabbatical and I was giving similar lectures in a couple of places. In Paris, it was 3 times more, I had 3 times more time and I did it on the board, okay? And at MIT, I was writing something on the board, but I am using slides also, right? And at MIT, I guess I had about the same time as here. So it should be fine, but I have to move a bit faster, okay? Anyway, so first thing I want to mention here is what kind of rate we can hope to achieve. What is minimax lower bound in this case, right? In functional estimation, if I put here this supremum over Hölder ball of smoothness set, okay? This is one of the results we obtained in this direction, okay? It's kind of in the situation when we have just a subset of RD, okay? A subset of RD, and we are dealing with regular statistical model. Here, regularity is meant in the following sense, that Kullback-Leibler distance between p theta and p theta naught, which is defined this way, and it's called in information theory relative entropy, is upper bounded by square of Euclidean norm between theta and theta naught, and we need this condition only locally in a small ball like this, right? In a small ball like this, and this is L infinity ball, right? With respect to L infinity distance, if you replace L infinity with Euclidean distance L2, then this ball will be a subset of the ball of radius r times square root of d divided by square root of n, right? R times square root of d divided by square root of n. This is minimax lower bound, and sometimes it's in the lower bound is better to put supremum over a small set as possible. So I'm putting over this L infinity ball. You can, if you wish, replace it by L2 ball of bigger radius, okay? But the important thing here is the structure of this bound. So in this bound, you have 2 terms. One term is of the order 1 over n. Another term is more or less of the order d over n to the power s, where s is the of the function. And this is really interesting term, because this term tells us that you might need to have more smoothness than 1, say, in order to be able to achieve 1 over n rate, okay? If d is or small of n even, right, we need, you might need to have enough smoothness to kill this term. Otherwise, it would prevent you from getting 1 over n rate, okay? 1 over n rate. Okay, so I will maybe say this one more time as it's, yeah. Sorry? Yeah, x1 and 2, yeah. No, you can write what will happen if you have, but it's kind of, under standard regularity, you will have two, right? So that's, yeah. Yeah, but no, but yeah, this condition is present all the time in statistics, right? The conditions that I wrote, and it's all the time present in lower bounds. It's not something unusual. Okay, I'm talking about functional estimation problem, and the meaning of this bound is basically the presence of this term. Okay, that is related to the degree of smoothness of the functional. Okay. So I don't know any other results where the term explicitly is present in this type of bounds, okay, in functional estimation. Okay, that's what I care about. Okay, so and then if you look at this, you will see that there is indeed a phase transition between fast rates, right, and to the power -1 rate will be fast for my purposes, right? It will happen when d is, for instance, is less than n to the power alpha for some alpha between 0 and 1, and s is larger than this threshold, 1 over 1 minus alpha, okay? And if d is at least n to the power alpha, but s is smaller, the rate becomes smaller, okay? So there is the same phenomena that was in this Ibragimov, Koltchinskii, and Nemirovsky paper in non-parametric case, right? But now it's related to how large dimension is, and depending on this, you need certain smoothness of the functional in order to achieve the rate. Otherwise, it's impossible to do. Okay, so the going to give you the proof of this bound. Maybe if I have time, it will happen at the end in a different framework, in the framework of covariance estimation, when this is a bit harder to prove, but I will show you this later, okay, if I have time. But my main focus will be on trying to show some methods that allow us to construct estimator for which this rate is attained. Okay, because it's a lower bound. Okay, maybe it's a bad lower bound, and it's even impossible to attain it. To get it, it turns out that it's possible in many cases to attain it, but you need to come up with some specific estimation methods in order to do that. Okay, so that will be the main content of the talk. Okay, now I will probably mention one more lower bound. This time it's not necessarily in RD with Euclidean norm. It will be in an arbitrary finite dimensional Banach space or linear norm space. And this bound can be viewed as a kind of non-asymptotic version of this Hayek-Lecam asymptotic local minimax lower bound. Okay, basically, there is this minimax risk here. It's normalized by the same variance, which is written in terms of the inverse of Fisher information. And then there is, in the lower bound, you have 1 here minus some stuff that could be made small. Okay, could be made small, and it will become small when you make n large and delta small, okay, simultaneously, but delta should not be too small. So delta square divided by n should still be large, okay? And then if your Fisher information matrix depends smoothly, so this continuity modulus tends to 0, and the derivative of your functional is also smooth, okay? So this thing will tend to 0, then you will get 1 in the limit. So from here you can, under the assumption I stated here, you can basically write down local asymptotic minimax lower bound of Hayek and Lecam. Okay, this bound will make sense to us in the case when 1 over n rate is attainable in the problem. Have enough smoothness of the functional rate, would be able also to show that estimation methods that we will develop will give us efficient estimator, okay, in the sense of Fisher-Hayek-Lecam. Okay, so that's will be kind of our goal here. And now I will start talking about one part of the important part of the construction of estimators for which the optimal rate are attained. And this is related to some higher order bias reduction methods. Okay, it turns out that the main reason why plug-in estimator based on maximum likelihood does not work, okay, generally in high dimensional problem is just because when you have a nonlinear function or nonlinear functional and you plug in some estimator that even is unbiased or has small bias, by plugging it in into nonlinear functional, you can increase bias dramatically, and this is very important when you are in high dimensional space, okay? Let's look at a very simple example which makes clear what is happening here. So we will look just at IAD observations and IAD observations sampled from standard normal distribution in RD with unknown parameter theta. The functional of interest is square of the norm of theta, okay, just Euclidean norm, okay. In this case, maximum likelihood estimator is, of course, the sample mean. And the plug-in estimator will be square of the norm of the sample mean, and it can be written this way. And then you can immediately, by straightforward computations, that basically boils down to computing this expectation, you can show that the bias of this estimator will be of the order d over n. Since the mean square as much as the square of we could not get anything better than d square over n square. D square over n square. So if d comes close to n, say, okay, already we could not have any hope to obtain 1 over n rate, right, for mean squared error. So we need to do bias reduction, okay? In this case, bias reduction is very simple, which is not true at all in general, okay? Why it's very simple here? Because we were able to compute bias and it happened to be just d over n. It even does not depend on the unknown parameter, okay? So in this case, we can just get rid of the bias simply by considering this estimator, just subtracting d over n here. And then again, it's a straightforward probability exercise to prove that the mean squared error will be given by this expression, okay? So we'll have this term, okay? This is what basically corresponds to what should happen, based on asymptotic efficiency, say, considerations, okay? And there is additional terms that depends on the dimension, but it's only on the order d divided by n squared. So it means that if d is smaller than n, we already have rate n to the power minus 1, okay? And if d is all small of n, then we have asymptotic normality like this. And this shows essentially the efficiency of this estimator, because this is what will be the optimal variance, okay, if you use different information consideration in this case, okay? This will be optimal variance. This is what should happen, okay? If d over n tends to infinity, then you still have asymptotic normality, but with different normalization, okay? So the error rate will be worse in this case, right? But that's the picture, okay, here, okay? So we want to have some bias reduction methods, okay, that would allow us to achieve more or less the same goal, but in more general situation in which, this kind of simple bias reduction like this does not work, okay? Okay, so we will discuss some methods in bias reduction that are often used by statisticians, okay? And this is all was known to statisticians for ages, okay? So in specific problems, okay, they were using something close to what I will describe, okay? Now, okay, so the first method actually is one of the most common and most popular methods. It is based just on Taylor expansion. So what usually you do, you split data into two parts, okay? say 1/2 of the data is used to compute some base estimator of the parameter, as I will call it. It could be, for instance, maximum likelihood estimator in your problem, okay? And then the rest of the data will be used to estimate the polynomial part of the Taylor expansion, okay? You can do it now conditionally on the first half of the data you used to compute this estimator, so you can view this polynomial as something non-random. Okay, something non-random. There is also remainder terms that will be bounded by this thing, where you have exponent s, and if s sufficiently large, and this is, say, not large, but say sufficiently small, but still can depend on dimension and things like this, right? Then you maybe for smooth enough functionals, you can make it negligible, okay? And the first part, you can try to construct unbiased estimator or estimator of small bias of polynomial function, right? And try then to show that this estimator has decent concentration properties and get maybe ideally 1/n convergence rate. Okay, that's kind of the way this is done usually in this type of problems. This is one of the most common ways of bias reduction. I am not going to talk much about this method. In some sense, you know, this method requires a bit more, okay, than I want to assume about the problem. As I said from the very beginning, I want to think about this problem this way, that functional is given to us only in the following sense, that there is an oracle that would tell me for a point in the parameter space of my choice what is the value of the functional at this point, and I can choose several points and get these values, okay? In this case, I need to know not only the values of the functional itself, I need to know, I have to ask oracle what are the values of the derivative of the functional, okay? This might be too much to ask in some cases, okay? That's why I will not focus much on this method also. It's a useful method, okay, in this type of problems. But I will discuss actually in detail, okay, some other methods. And one method that I will discuss is the method based on approximate solution of what I will call bias equation. Okay, so if you want, the idea would be this. Okay, so plug-in estimator is bad, so it's bad to just apply functional f itself to some base estimator, for instance, MLE, right, theta hat. But what if instead of using f of theta hat, we will use g of theta hat for a properly chosen function g? Okay, and we are trying to choose function g such that, for instance, ideally such that expectation of g of theta hat is just equal to f of theta. In this case, we will construct unbiased estimator, okay? And this is, by the way, one of the most common ways to construct unbiased estimator in standard theory of unbiased estimators in statistics, okay? Basically, in reality, it boils down to solving some integral equation, okay? Solving some integral equation. For instance, Kolmogorov in the late 40s wrote a paper on unbiased estimation that was just focused on reduction of these problems to solving some integral equations, okay? So in our case, we don't always have a solution, exact solution of integral equation, but we will try to replace it by some approximate solution, okay? One should be kind of careful here, because when you solve integral equation, if the right-hand side is smooth, the solution is not necessarily smooth. We are applying integral operator to g, right? And this is an inverse problem, right, in this case. And the solution g is not necessarily that smooth, okay? We don't want to lose too much smoothness, because we want also to have concentration properties, okay? Bias is only one part of the problem, but we need to have, you know, g should be at least Lipschitz, okay, in order to have decent concentration properties in this type of problems, or even more, okay? But we kind of have to be careful, okay, when we are using this method. Okay, so this will be one method that I will discuss. Another method that we will get to this method next time is based on a completely different idea. The idea here is to kind of choose several sample sizes smaller than n, and for each of these sample sizes to compute a base estimator. Okay, so we are using a base estimators with different sample sizes, and then we are looking at linear combination of these plugin estimators, okay, several plugin estimators. And what we are trying to do, we are trying to choose sample sizes and coefficients in such a way that biases of individual plugin estimators essentially cancel themselves out, okay? So that's the trick here, okay? We are trying to cancel out these biases and create linear combination like this that would have small bias and decent concentration properties, okay? We will discuss this next time, okay, how to do this type of things. It's also a very actually traditional method of bias reduction in statistics. Also, maybe the version of this method that I will discuss will be slightly different, okay, than what is common in the literature, okay? Now I will get back to the previous method, and we will actually spend lots of time discussing this previous method, okay, in detail, because it actually leads, surprisingly enough, I never thought of bias reduction problems as problems where there is any interesting mathematics involved, okay? But I was wrong, okay? And actually, you know, I mentioned here a quite interesting paper. Let me get back to this because I have not said this, okay? There is a quite interesting paper by Zhao and Han published in 2020 in IEEE, Transactions on Information Theory. They were actually interested in estimation of some functionals in high-dimensional statistics. They're information theory guys, and were interested in estimation of entropy, for instance, okay, or on some alphabet, okay, and stuff like this. But they discovered that this bias reduction problem is important in these problems, and they wrote a paper that review a number of methods used by statisticians for bias reduction, and they intentionally do it in the case of a very simple model, not high dimensional at all, IID Bernoulli with unknown parameter theta. Okay, just one-dimensional parameter, okay? And they discovered that this problem in the case of this simple model, when you are interested in some subtle properties of this method, they immediately lead you to some interesting problems, sometimes unsolved problems in approximation theory, for instance, okay? So there are many connections of this method to various stuff in mathematics, so I will hope to show you some of these connections, not the same as in this paper, okay, in what follows, okay. So let's look at some iterative approach to solving this bias equation, as I called it, okay? So again, this will be our standard framework. We have IID observation sample from distribution with unknown parameter theta. Everything is in some Banach space, and there is some estimator based on the data. I will call it base estimator. I will assume that the error of this estimator defined in this sense is of the order square root of d over n, very typical situation in statistics. D is dimension or some complexity parameter. It does not matter for me what d is, but it could be large, say, okay, that's the framework. And then ideally what we want to do, given a smooth functional defined on the parameter space, we want to find g such that it approximately solves bias equation with the error of the order n to the power minus 1/2. And we also want to keep concentration also on the scale n to the power minus 1/2. If we are able to do this, we will ensure that this functional can be estimated with square root of n rate, okay? The square root of n rate. So that's the idea of this approach. Now, the first reference to this approach I was able to discover, I actually discovered it on my own, but then I learned that, that it was known, of course, nobody, you could not discover anything in this type of thing. The earliest reference I was able to find was in the paper by Peter Hall and Martin published in 1988. Okay, and it was kind of, they called it iterated bootstrap because it was kind of time when bootstrap was very active area, okay, of research, bootstrap methods in statistics, and it was related to bootstrap in this paper, okay. But the idea is the following: what they what they are doing, okay, first iteration for us will be plugin estimator based on some base estimate. And plugin estimator is biased, and this is bias of plugin estimator. Okay, it's some function of theta that, in principle, if we know statistical model, we know this function also, right? If we know our functional and know statistical model, then this function is given to us. Okay, is given to us. So what can we do? We can kind of do a very straightforward thing. We can try to improve this estimator, do first order bias correction. We are trying to improve this estimator by subtracting plugin estimator of the bias. Okay, plugin estimator of the bias. But then the a plugin estimator of the bias, okay, plugin estimator of the bias. So this is estimator of this guy, right, is biased itself, right? And its bias will be basically square of this operator B applied to function F, okay? Applied to function F. And then you might want to do second order bias correction, okay, and to add to this B square, okay, f of theta hat, okay, and so on, okay. You might need to do it several times in order to eliminate bias. Of course, despite the fact that we know this function, right, b of theta, it's kind of integral, okay. It will be some multivariate integrals that need to be computed, even if we know the model and know everything, right? And it might be a bad problem to do, okay. What they basically do, they give some way to compute this updates, okay, iterative updates of the estimator using Bootstrap and Monte Carlo simulation. And we will see how it works later, okay, not the way they wrote it, but the way I wrote it for my purposes, okay. We will see later why it is related to Bootstrap, okay. But I actually prefer, the way I myself looked at this problem even before I discovered this paper of Hall and Mammon, and it's more analytic way, okay? It's more analytic way. So basically what we are looking at here, we are looking at this operator. Let's remember this notation because I will use it a lot, okay? Tg of theta is defined as this expectation, and we can write it as integral operator with respect to certain Markov kernel defined on the parameter space, right? And this Markov kernel is given by this formula, so it just gives us the distribution of our base estimate, okay? It's could be viewed as a transition kernel of Markov chain, and we will create this Markov chain later, okay, because it will be of importance to us. Okay, now what we want to do, we want to find an approximate solution of this integral equation with this type of order. What is kind of a very old 19th century method of approximate solution of integral equations? This is a method based on what is called Neumann series, okay? So essentially what you are trying to do, you are defining this operator B, which is T minus identity, right? And if B is kind of small, then T, which is I plus B, we can invert it, right? And the inverse will be written as this geometric series, right? This is showed you before, okay? So it's kind of related to this 19th century method of approximate solution of integral equation, okay? That goes back to Neumann, okay? I want to emphasize that this is not von Neumann, okay? Because some referees of my papers, when I wrote them, started trying to make me to have some respect to von Neumann and not drop von from the name of von Neumann, okay? But it's not von Neumann, of course. It's Karl Neumann, who lived maybe 100 years earlier, okay, a German Prussian, actually, mathematician of second half of 19th century, well-known mathematician, you know, Neumann boundary conditions for PDEs, you know, this is goes back to him, and Neumann series also. He did some foundational work on integral equations back then, okay? Okay, so now so basically, after k iterations, we are getting function fk this way, right? And fk of theta hat becomes our estimator, okay? After k iterations, right, of bias reduction. And the bias of this estimator can be easily expressed in terms of k plus first power of operator b. Okay, it just follows from these formulas in two lines, okay? That this is the fact. So basically, we need to know what this case power is. If we are able to show that this k plus first power is equal to 0, then it means that we constructed an unbiased estimator. Otherwise, we need bounds on this. Okay, that's basically what is happening here. Okay, so it is kind of turns out not to be very easy analytic problem to understand what is happening in this situation with these powers. And let's start first with a model in which it is rather simple, okay? It is rather simple, and this is a location model. So we are assuming that our distribution p theta is just a shift, right, of some probability measure p, okay, on our space, and theta is location parameter, okay? Then we have IAD observation sampled from p theta. So location parameter is the only unknown thing. P is known to us, okay? That's the assumption here. Then in such problems in statistics, we usually like to use equivariant estimators of location parameter. And let's assume that we are in possession of an equivariant estimator. So equivariant means that, you know, this equivariance with respect to location group, with respect to group of translations of the space, right? So it means just that when we are adding the same vector A to all entries of this function, right, the function changes this way, right? This is what the properties that the sample mean possesses, or sample median, for instance, right? Okay. That's kind of natural property when you deal with location models, okay, in statistics. Okay, but now using this property, we can write our estimator theta n of x1, xn, xj can be written as theta plus eta j, so it's parameter plus some noise, and these are IAD variables sampled from distribution P now, right? And we can write this guy as theta plus theta n hat of eta 1, eta n. It follows from equivariance property, right? And let's call this psi, right? Let's call this psi. And then we can forget about the data. This we can assume that our data is just this one single observation, right? The value of this estimator, right? The value of this estimator, and this will be unknown parameter theta plus some noise whose distribution does not depend on parameter. Okay, plus some noise whose distribution depend on. So we are kind of can work with one observation model as instead, okay? And we'll call it random shift model, okay? We can also, without loss of generality, assume that this noise has zero mean, okay? And this assumption is reasonable because we know, since we know distribution P, the only unknown thing is parameter, and P does not depend on the parameter. Expectation of this guy Xi, right, does not depend on theta, right? So it's known to us. We can basically subtract it and adjust the model a little bit, right, and work with the model in which the noise has zero mean, right? Okay, so we will make this assumption. Okay, so let's start with this, as I will call it, a random shift model with zero mean, right? With zero mean. So instead of estimator, we have now just one single data point, and this is our estimator. Okay? It's our estimator in the simplified notations. Now, operator T in this case becomes just this operator, right? This will be operator T, right? Our operator T. Now, let's see what will happen with operator T when our functional is very simple, when our functional is a polynomial on our space E. Okay, if it's a polynomial, it turns out that both TF and BF, B is T minus identity, right? Both TF and BF are also a polynomial, and degree of TF will be same as degree of F, and degree of BF will be degree of F minus 2. So it's a very simple algebra to see that this is the case, because it's enough for us to consider only monomial like this. So what are polynomial of Banach spaces? We can start with monomial, which means that we start with M linear form, right? Linear form, it has M entries. We are making this entries equal, and we are getting homogeneous polynomial of degree M as a result, right? Homogeneous polynomial of degree M as a result. Arbitrary polynomial on vector space will be sum of such homogeneous polynomials, okay? So it's enough just to look at one guy like this. And for this guy, we can write f of theta plus xi, this is what is involved here, as f of theta plus these m terms, right, where we replaced theta by xi in one place, right, plus some remainder. Right? And remainder will be clearly polynomial of degree m minus 2 with respect to theta, because in the remainder, in each term in the remainder, psi will be present at least twice, right? And theta will be at most m minus 2 times, right? At most m minus 2 times. So the degree of this is m minus 2. The expectation of this guy will be 0, because psi has 0 expectation, and this is linear with respect to psi, right? So all this guys will vanish when we compute the expectation. So if we write T f of theta, it will be f of theta, Tf of theta minus f of theta is Bf of theta. So Bf of theta will be polynomial of degree m minus 2, and Tf of theta will be of degree m. Okay, still, okay, so that's what we have here. Now, if we now look a bit more carefully at what is happening here, if you don't know space, how space lesser or equal than m, right? Lesser or equal than m. Then what we said before is p map and p maps pm into pm minus 2. So p is a little bit like the now back to term, right? It becomes finite sum, and it automatically gives us the inverse of operator t, right? So the operator t in this case is invertible with inverse given by this finite sum that is equal to the whole. And then it also means that in this case, fk of x is an unbiased estimator of theta for all polynomials of degree m, right? If k plus 1 is bigger than m over 2. Okay, that's what is happening here. So this procedure gives us unbiased estimator in this case, okay? In the case of random shift models like this. Okay, let's look at even one more useful property of this operators, okay, that we are dealing with here. If you look at the case when E is RD, d-dimensional Euclidean space, say, and Xi is vector with independent components. This is the noise vector, right? It has independent components in this case, okay? Let's assume this includes any normal model, because per normal model you can find always a basis, right, in which it becomes model with independent components, right? You can use the standardization property in order to figure out how operator T acts, okay, in this case. Okay, so let's look at the case of normal model. They're just simple examples. Let's look at the case of normal model. So we will assume that we created a basis in which the components are independent, right? The components are independent, and then since operator T tensorizes, it's enough to study this problem only in the case when D is equal to 1. Okay, so we'll assume that the noise is just standard normal random variable, otherwise things this then with identity false, right? And if we now write this expectation that we have here as DJF times 1, which it is, right, in the space O2 with respect to Gaussian measure, this expectation will be equal to this, then we can move dj as adjoint, right, to another site, and we will get some function here, right, some function here that I denoted here aj, and it's easy to figure out that this function aj will be just a Hermite polynomial, okay? The second way to use this is how people define them in quantum mechanics, for instance, traditionally, okay? They define them in terms of these two operators, essentially, okay? Okay, so this is now if we look back at these formulas that we wrote here and replace this by this inner product, right? Then TF will be written in this form, right? And we also know that Hermite polynomials are orthogonal, and using this orthogonality condition, we can just decompose function f in terms of Hermite polynomial, because f is polynomial of degree m, right, in our case, and it can be written in terms of Hermite polynomial as Fourier series, right, with respect to this orthogonal polynomials, and it will be given by this expression. If you compare this expression with this expression, you see what operator T does, right? Operator T in this case maps linear combination of Hermite polynomial into linear combination of powers, right? Into linear combination of powers. And the inverse of operator T for function f, which is just this polynomial, will be equal to this. And this gives us will be obtained by this, and it will be equal to this function fkx that we observed earlier, right? So this method that we discussed, right, this Neumann series method gives us this answer in this case, and this is well-known answer in statistics, okay? How to construct unbiased estimator of polynomial based on IID distributions from standard normal model. Okay, you will need from model with variance 1, right? You need to replace powers by Hermite polynomials. Okay, in this case by Hermite polynomials of the same degree. Okay, it's well-known fact in the theory of unbiased estimation, but it just can be explained in terms of this Neumann series stuff. Okay, yeah. Mhm. Might be, or everything is related to everything. Right. Okay, so now using the tensorization property, right, that I discussed, you can easily extend this to d-dimensional case, right? In this case, to estimate this guy f of theta, which is say polynomial of degree n, you need to use fkx for k plus 1 bigger than m over 2, right? And this will be given by this expression, right? There is some dependence on the variances now. It's kind of easy to figure out from all these relationships that I described, okay? And from tensorization property, okay, that there are multivariate versions of this. Okay, so this is, of course, was a very nice example of Gaussian model, right, in which case you can do a lot and you can compute these things explicitly, okay? But in general case, it's not true that you can compute it explicitly, but still, if you are looking with arbitrary random shift model, okay, the one that I discussed, okay, with noise that is not necessarily Gaussian, it can be arbitrarily mean zero noise in any Banach space, actually, okay, in any Banach space. You still can easily write certain representation formulas for the powers of operator T and operator B. And for operator T, this is just this representation. This, no. Oh, uh, K time differentiable, then bkf can be computed by this formula. It's expectation of fk, right? It's differentiated with respect to all the centers, so the derivative is in this direction. I will try to show you the proof of that fact. Okay, it's a simple, but I think nice proof. Okay, the and why I need this proof, because I will later show some more complicated functions. It will be very similar in many respects. Okay, so now let's look at this function phi of t1 tk, which is just f of theta plus sum from I equal 1 to k ti xii. Now t1 tk will be vector from k-dimensional unit cube. Okay, from k-dimensional unit cube. Let's consider this function. Then the first observation is that for any j less or equals than k, if we consider t1 tk from which will be a vertex of the cube, so it has coordinates that are either 0 and 1, and it's such vertex that the number of coordinates equal to 1 is equal to j, right, is equal to j. Then tj f theta can be written as expectation of this function, okay, for any such vertex, okay, for any such vertex. Why? Because, you remember what is tj f theta, right? By the formula that I showed you before, right? Okay, TK f theta is obtained this way. You need to compute expectation of f theta, and here add sum of k independent IAD copies of noise psi, right? Of noise psi, and when we are doing this in this function phi, we are doing essentially the same, right? Since all coordinates are zero except j coordinates, we are adding j independent copies of noise psi still, right? It's a kind of different copies, but it does not matter for computation of the expectation, right? It will be just equal j of theta, right? J of theta. Now, what we do next, we let me write the whole thing. So bk of f theta, b is t minus I, so we can use, we have here t minus I to the power k. We can use Newton's binomial formula to write down this, right? Now we have tj of f theta here. Now there are k choose j of them. I can replace this k choose j by this sum over all these vectors which have exactly j and expectation for each choice of such vector is exactly the same. So I can replace this product by this expectation. I can now pull out expectation, and I have certain sum of the values of my function. But now we just have to try to recognize what this expression is. Okay, what this expression is. And it turns out it's very easy to check that this expression can be written in the following form. If I introduce discrete differentiation of my function defined on binary cube now, right? Defined on binary cube. This discrete differentiation, what I'm doing, I'm changing one variable, right, between 1 and 0 and subtracting here, okay? I'm getting increment along one of the sides of the cube, right, of my function. This is this operator delta I. Then you can easily see that the sum written here will be just the result of this discrete differentiation. But now if our function is k times differentiable, I can write this using kind of k-dimensional version of Newton-Leibniz formula, okay? In dimension 1, we write integral of the derivative will be equal to the increment of the function, right? If we write integral of the derivative from a to b, if we apply it to each coordinate, right, Newton-Leibniz formula, we will get that this integral is exactly equal to this expression, right? So as a result, we are ended up with this integral of this function, and it remains to differentiate now a function phi, right? If we differentiate function phi, and the derivative of function phi is exactly equal to k's derivative of f in this directions, right? And this is what was present formula that I wrote before, okay? That I wrote before. So as a result, we are getting basically this expression, and now I can replace TJs by IAD uniformly distributed. Okay? So that's basically some integral representation, right, for this operator bk f of theta, which is rather easy to derive in this setting, right, in the case of random shift model. Okay. Now, why these representations are useful? These representations are very useful for us because they allow us to compute further derivatives if we need of functions bk f of theta, for instance, okay? And using the expression on the norms of the We can also easily derive bound on the bias of the estimator fk of x, right, in this case, right? And this bound will be of this order. And all this follows from this integral representations, right? All this follows from this integral representations. You remember that the bias is can be expressed in right? That's why bounds on the bias follow from these considerations. Okay, so now if we go back to location parameter, so we have equivariant estimator of location parameter theta. Psi in this case is just theta n hat minus theta, right? Theta n hat minus theta. And if for our estimator we have, say, this standard bound, then you would end up with this bound on the bias, okay? You would end up with this bound on the bias, okay? That's basically how it works and how this method can be used in order to reduce bias, okay, to reduce bias. In the case of location families, okay. Now, what to do if we are dealing with a more general model, okay? With more general model, it's not necessarily now location model, it's more or less arbitrary model, okay? How to do something similar to what we did in the case of location model in this case, okay? In this case. So I'm assuming again that I am in possession of estimator theta hat, for which, say, this type of bound holds. D is dimension or other complexity parameter. I remind you that I define this operator this way, and it can be written in terms of Markov kernel now, okay? In terms of Markov kernel, and this Markov kernel gives us the distribution of estimator theta hat, right? Let's now try to use this Markov kernel in order to run Markov chain, okay? So I will create a Markov chain with transition probability kernel P theta A, okay, P theta A, that starts at our unknown parameter theta, so theta hat 0 at moment of time 0 is theta, and then it moves to theta hat 1, which will be theta hat, okay, at the next iteration, right? And then at the next iteration, according to this kernel, it should move to a new location theta, what this chain is, probabilistically, and what is more precisely statistical interpretation of this chain. You can easily figure out how to implement this chain. Indeed, you start with initial location of the chain is theta, right? It's theta. Then what you do, you sample NIAD observation from distribution P theta and compute estimator theta hat. Okay, this is where the chain moves at the first step. This is theta. Then, in order to create theta hat 2, in order to keep the same transition probability kernel, what you would have to do, you would have to use theta hat as new value of the parameter, resample n observations from the distribution with parameter p theta hat, right, and compute your estimator based on this resampled data. This is what is called parametric bootstrap in statistics. This procedure is parametric bootstrap in statistics, right? This resampling procedure is parametric bootstrap. And then in order to move to theta hat 3, you have to iterate this bootstrap. You have to use theta hat 2 as parameter, resample the data and observations from distribution with parameter theta hat 2, right? And compute your estimator again based on resampled data, and this will be theta hat 3, and so on. Okay, and so on. So basically, this chain, I call it a bootstrap chain because indeed it is based on iterative application of parametric bootstrap to our problem. Okay, to our problem. Okay, now what is how this bootstrap chain is going to work in our case? Okay. We can now easily write the same way as we did in the case of random shift model, okay? It's a special case of what we are doing now, right? We can write formulas for operator t to the power kf, it will be expectation of f theta hat k. This follows just from Chapman-Kolmogorov equation, actually, for our Markov chain, right? It's not anything complicated. Now, bk of f theta hat, again, by using Newton's binomial formula, right? By using Newton's binomial formula, we can write it this way. And then, because Tj of f theta can be written as expectation of this guy, we can write it as expectation of this expression, right? Of this expression, right? And this expression that we have here is nothing but the case order difference of our function f computed along the bootstrap chain, right? So we kind of compute that function exactly. We can also write, using very simple combinatorics, we can write function fk of theta that gives us our estimator as expectation of this expression, okay, as expectation of this expression. So this is not the way Hall and Martin explains this, okay, but you can now use this formula in order to compute fk of theta hat, okay? Fk of theta hat using bootstrap and Monte Carlo simulation, because it basically means that in this expectation you have to replace theta by theta hat, which means that we are starting now on our bootstrap chain not from theta but from theta hat, right? And we are starting our chain from theta hat. We can repeat segment of the chain of length k many times, right? And we can compute this expectation by Monte Carlo. Okay, by Monte Carlo averaging, and this is basically what they were trying to do in this paper, but they were not explaining it in this way. Okay, now let's recall. I have to finish in 5 minutes, so let's recall a very simple fact from classical calculus. Okay. If we take k times differentiable function, we can define this first order difference operator delta h, okay? Delta h, okay? Applied to f, it will be f of x plus h minus f of x, kind of discrete differentiation of our function. If we raise this operator to power k, it will be given by this expression, right? f of x plus jh correspond more or less to f of theta hat j, right? In the formulas that I wrote earlier. Okay? Again, we can view this motion in the real line from x to x plus h to x plus twice h and so on as a very simple deterministic Markov chain. Okay, deterministic Markov chain, and then this thing would be exactly the same as the things that I wrote before. Okay, the things that I wrote before for this bootstrap chain. Okay, now it is well known from classical analysis. Okay, that this case order difference for k times continuously differentiable function can be written this way. So it will be of the order h to the power k. Now, the question that we will have to answer is that if we are dealing with our bootstrap chain, for which we will have this condition, actually, right? Because we assume that for estimator itself, we have condition like this, can be translated as condition on the bootstrap chain, right? It will be the same for bootstrap chain, and it will be of the order square root of d over n. If this is kind of small, if d is not very large comparing with n, okay? Comparing with n. This is kind of small. Is it true for that for d less than n and for f in ck, bk f of theta will be of the order square root of d over n to the power k? The k of theta is expectation, right? Expectation of the case order difference along the bootstrap chain, right? So if the world is a fair place, right, and we have the same for this kind of more complicated dynamics in our parameter space, defined in terms of this bootstrap chain, right, as what we have in for the simple dynamics when we move along straight line, with jumps of size h, right? If the same is true for in this case, then we have just justification of the method of bias reduction in this case, okay? And that's basically what we will have to understand, okay, next time, probably, because we don't have time anymore, okay, today.